right, welcome to the naming practice review. We're going to go through just some additional problems for naming compounds, focusing on ionic compounds and naming acids. This is nothing new from what we've done in class. It's just a little bit of extra examples to give you some help while you're going through it. So, naming compounds. If you've got an ionic compound, which these all are, then we name the compound by naming each of the two ions individually and then sticking it together. So when you see the first one, NaNO2, the metal is one of the ions. The rest of it is a polyatomic. If you see three elements together and you identify this as being an ionic compound, you do not give it three elements names. No, it's going to be one element and a polyatomic, possibly even two polyatomics put together. So it's going to have two words. So we're going to name these two things. Cation always comes first, anion always comes second. So first up is the Na. Well, that's easy enough. That's sodium. That's going to be the first part of our name. Some questions we need to ask. Can sodium have multiple oxidation states? It's in group 1. No, it cannot. That means that we do not need a Roman numeral here. We don't need to worry about what is the charge on the sodium because it's only ever going to be +1. So that takes care of the Na. Now we're going to name the NO2. Here is where you cannot do naming unless you have polyatomic ions in your brain. You have to know polyatomic ions. Now, the list that I gave you to memorize is not all the polyatomic ions because I'm not asking you to memorize all of them. I'm asking you to memorize some of them and then use the rules to figure out the rest. NO2 is not an ion that I asked you to memorize. However, it is related to one that I did ask you to memorize, which is NO3. NO3 is nitrate. But we don't have nitrate here. We've got NO2. It's got one less oxygen than 8. So what we do is we change the suffix. Instead of 8, it's going to be ite. This is sodium nitrite. So we split it into the two ions. We name each of them individually, simply put them together, and that is the name of our ionic compound. This is sodium nitrite. Next up, ZN3P2. Again, this is ionic. It does not involve any polyatomics, so we're just going to name each of these things, the Zn and the P, and then put that together. That's going to be our name. Well, Zn, the cation, is just the element name, so that's just zinc. But then we need to think, can zinc have more than one charge? It is a transition metal. I told you, I asked you to memorize two transition metals that only have one possible charge, and one of them was zinc. Zinc is always +2. It's never going to be anything else. We're going to get to the reason to that when we talk about periodic table and electron configuration. But zinc is always going to be +2, so we don't need any Roman numerals, which means that I can go on to the P and name that. P is phosphorus, but this is not zinc phosphorus. When you've got the nonmetal as a monatomic anion, then we have that "ide" ending. So phosphorus is going to turn into phosphide. This is zinc phosphide. Next up, CuO. Again, this is ionic compound, so we're going to name each of these two things individually and put them together. Cu, that's copper. Asking the question, can our metal have more than one charge? Yes, it can. Copper is a big one that has multiple charges. It's going to have two possible charges that hopefully you're going to pick up throughout the year, which means that we need to actually assign oxidation numbers. We need to figure out what the charge is on the copper in CuO. And the way we're going to do that is by knowing what the charge is on the other element. The other element is oxygen, and hopefully you remember that oxygen is -2. Like 99% of the time when it has a charge. I know it's -2 because, first of all, you could hopefully either remember that particular rule from Regents Chem, which is a really big one about assigning oxidation numbers, or you can look at oxygen's position on the periodic table. It's in group 16. That means that it has 6 valence electrons. It wants 8, so it's going to gain 2 more. Gaining 2 electrons, that's a charge of -2. Then we look at the ratio. It's 1 to 1. 1 copper for 1 oxygen. Charges have to cancel one another out. And ionic compounds as a whole do not have a charge. They're composed of things that do, but they themselves overall are electrically neutral. That means that the charge in the copper has to be +2 in order to negate the -2 coming in from the oxygen. So we're going to put a 2 in Roman numerals right after the copper. Copper can have multiple charges. In this case, its charge is +2. And then we name the oxygen. This is a diatomic compound, binary compound, excuse me. 2 elements. So I'm going to simply add "ide" to the end of the anion. So oxygen, it's not going to be copper-2 oxygen, it's going to be copper-2 oxide. And then the last one, FeBrO4 sub 2. Again, we're naming each of these things individually, and we're going to then figure out, just put them together, and that's going to be our overall name. So first up is Fe. That's easy, that's iron. Then we ask the question, can iron have multiple charges? It's a transition metal. It's not one of the 2 transition metals I asked you to memorize. It's only having 1 charge. Therefore, yes, it can have multiple charges. Yes, we are going to need to figure out what the charge is on the iron. And the way we're going to do that is by having a look at the other ion, the polyatomic, BrO4. All right, so let's deal with the charge first before we get into naming. I did not ask you to memorize BrO4. However, I did ask you to memorize ClO3, which you might be saying, but that's pretty different from BrO4, Mrs. Julian. And then I'm going to tell you, actually, no, it's not. Because remember, all the halogens behave exactly the same way. So if chlorine does one thing, then bromine is going to do the same thing. And that exact same way extends to the charge on the polyatomic ion. ClO3 has a charge of -1. That means that all the other polyatomic ions that are based off of ClO3, like ClO4, also has a charge of -1. Remember, the overall charge of the polyatomic ion does not change if you're simply changing how many oxygens are in it. As long as you're keeping that central atom the same, the charge will stay the same overall. So because ClO3 is -1, that means that ClO4 is -1, which means that BrO4 is -1. I haven't named BrO4 yet, I'm just thinking about its charge. So that means that BrO4 has a -1 charge. And then we're going to look at the ratio between these 2 things by looking at the subscripts. Right, subscripts here and here. So there are 2 BrO4s for every 1 iron. And again, the BrO4 has a charge of -1, which means that the Fe has to have a charge of +2 in order to cancel out the 2 BrO4s. So this is iron 2. Now we're going to actually name BrO4. Kind of giving it away a little bit about what we're going to do, but this is the thought process that I want you to go through. I'm going to do this, write this up over here on the right. ClO3. I asked you to memorize that. That's one that you have to memorize. ClO3, what is it? What is its name? This is the chlorate ion. Memorize that. ClO3 -1 is chlorate, and then memorize rules. So if ClO3 -1 is chlorate, then BrO3 -1, simply swapping out halogens, well, that's bromate. Okay, that's getting us closer, but we're not exactly there yet because we don't have BrO3. We've got BrO4. We've got 1 more oxygens. More oxygens. We want to bring in that prefix per. Because prefix per, remember, it comes from hyper, like a hyper 3-year-old running around. They got so much energy, they're crazy. Per comes from hyper, so BrO4 -1 is perbromate. So put that together, we've got our name. This is iron 2 perbromate. Going on, naming some acids. Because acid naming rules can be a little bit difficult, so we might need a little bit of practice, and that's perfectly fine. First up, HC2H3O2. I can identify this as being an acid because it starts with an H. There are 2 components of this acid, the H and everything else. The H out in front means that it's an acid. The C2H3O2 is a polyatomic ion. Acid names are based on the polyatomic ions that they come from. You have to know polyatomic ions. So this is a polyatomic ion I asked you to memorize, C2H3O2. Pull that up, bring it up in your brain. Oh ho, this is the acetate ion. That is not the name of the acid, that's the name of the polyatomic ion, because acid names are based on ions. So we think of our acid naming rules. Great, you've got the polyatomic ion. We need that. 8's become X. We change the suffix at the end. Eights become X. So instead of the acetate ion, by sticking that H on front, we've made it an acid. This is acetic acid. Next up, H3PO3. Again, acids, two parts, the H and everything else. In this case, the everything else is PO3. What's the charge on this PO3? It's -3. How did you know that, Mrs. Julian? Well, I looked and I saw that there were 3 H's. Each H is +1. Right? H is always going to be +1 when it's in an acid out in front. So the PO3 has to have a charge of -3 to compensate for the 3 hydrogen ions that it's got attached. Okay, so then we need to focus on naming PO3. I did not ask you to memorize PO3, however, I did ask you to memorize PO4. PO4 is phosphate. That's not what we have, but it's what it's based off of. Phosphate is PO4. We've got PO3, one less oxygen. One less oxygen, that's phosphite. What do we do with ite endings when we have an acid? Ites become us. Ites become X. Ites become us. So instead of phosphite ion, what we have here, this is actually a little bit of an exception. This is called phosphorus acid. It is not pronounced phosphorus like the element. The emphasis is on a different syllable. It's actually pronounced phosphorus acid. Now, I will add right here that if you wrote down phosphorus acid because you said phosphite, and so you just simply took off that ite and added OUS, I would not take off for that, because that shows me that you know the naming rules, you're very comfortable with them. So this is a little bit of an exception, and I am not going to be nitpicky about it. If you put phosphorus acid, that would be absolutely acceptable and no points would be deducted there. Next up is HI. Two parts of this, H plus and I minus. This is a binary acid. This does not have a polyatomic ion in it. When we name binary acids, we use the hydro prefix. That's how we indicate. That's one of the ways we indicate that we have a binary acid. So this is going to be hydro, meaning binary. And then you need to say what it's binary with, because we know it's H. Acid always is going to mean H. So then it's the I. So this is going to be iodo. Well, we're going to have the ic ending. And the word acid. Binary acids have a hydro prefix and an ic suffix. So this is hydroiodic acid. Think hydrochloric acid, right? That's HCl. That's the one that you should hopefully feel very comfortable with. You've been seeing hydrochloric acid probably since middle school, and hopefully you know that it's HCl. Well, this is just swapping out a halogen for another halogen. So instead of hydrochloric, it's going to be hydroiodic acid. Important to remember, though, that this hydro prefix is a major way of indicating a binary acid. And the last one, HClO, always two components of the acid, the H and everything else. This is not a binary acid. This is based off of a polyatomic ion, so we have to name the polyatomic ion. Ion naming series. Chlorate, ClO3, -1. Ask you to memorize that and then memorize the rules. This is not chlorate, though. Take away one oxygen, what do you do to the name? Change the ending. This is chlorite, right? Ite means one less oxygen than 8. But we don't have ClO2 minus, we have ClO -1. So what do you do when you take away an additional oxygen? You add a hypo to the front. This is hypochlorite. Hypo, like hippo, way less energy, very much less. So what we have right here is the hypochlorite ion. And we have it in terms of an acid form. We're going to go back up to this rule right here. Ites become us's, and that's exactly what we're going to do here. Ites become us's. So instead of the hypochlorite ion, and you stick an H plus out in front, this is going to be hypo, that's an H, chlorous acid. You're keeping that hypo out in front. That's important because that's indicating how many oxygens we have in the compound, and simply changing the suffix there to make it hypochlorous acid.